Hello everyone, my name is Victorin. In this video, I will be presenting about the approaches to apply Penman-Monteith and FAO FP6 methods using remote sensing data. Remote sensing data has been utilized to estimate evapotranspiration since the 1980s. The main approach was applying surface energy balance methods or relationship between land surface temperature and vegetation index. Since 2007, models that solve Penman-Monteith equation using remote sensing data have been developed. The main advantage of Penman-Monteith equation is reducing explicit dependence on thermal remote sensing for land surface temperature estimations. Since Penman-Monteith equation can be applied at different time steps, it is considered more reliable to provide spatially and temporally continuous ET, which is important for operational applications. Moreover, Penman-Monteith is applicable even in water-limiting conditions. The success of applying Penman-Monteith using remote sensing data depends greatly on accurate estimation of surface resistance in the equation. Many approaches have been developed to estimate surface resistance from remote sensing data. Since the surface resistance is different for canopy and soil surface, most Penman-Monteith models use some methods to separate canopy and soil resistance using vegetation fractions. These models are also called two-source model. Vegetation fractions can be estimated using vegetation indices and land cover data from remote sensing. For soil surface resistance, it can be scaled from potential wet soil evaporation, which is estimated from radiation data. In some other models, it can also be estimated from soil moisture data. For canopy surface resistance, there have been many approaches developed. For example, the earliest model is scaling stomatal resistance using leaf area index. Stomatal resistance depends on the type of vegetation, which is based on land cover data. Another model that is commonly used is Jarvis-Stillworth, in which canopy resistance is a factor of maximum canopy resistance, and it depends on the stress factors from temperature, vapor pressure deficit, radiation, and soil moisture. For aerodynamic resistance, most models apply the traditional equation in which aerodynamic resistance is an expression of obstacle height, displacement height, roughness length, and wind speed. Different remote sensing based models have different approaches to estimate these parameters. However, most of them use vegetation indices and land cover data from remote sensing. And of course, this approach requires wind speed data from meteorological datasets. Penman-Monteith equation was developed for ground-based estimation of evapotranspirations, where net radiation is often measured by net radiometer. However, for remote sensing-based estimation, no satellite sensor can directly measure net radiation. Therefore, it is estimated from other data sources. The most important remote sensing input to estimate net radiation is albedo, which partitions short-wave incoming radiation to net short-wave radiation. For net long-wave radiation, there are two different approaches. The first approach depends on land surface temperature to estimate the outgoing long-wave radiation. This means Penman-Monteith equation is considered radiative coupled. The second approach approximates net long-wave radiation based on air temperature, air pressures, and humidity. Similarly, ground heat flux cannot be measured directly from space. It is usually estimated from net radiation by characterizing the ground surface using temperature, vegetation, and moisture data. Here is an example of MODIS16 evapotranspiration algorithms. In this flowchart, you can see what type of remote sensing and meteorological inputs are used in the model and for what intermediate variables. In case of global models, meteorological data can be estimated from gridded data of dense in situ measurement network or from global climate models. Another approach to estimate ET from remote sensing and Penman-Montis equation is by applying FAO 56 standard equation. The reference evapotranspiration is calculated using parameters estimated from remote sensing and meteorological data. The crop coefficients can be estimated and spatially distributed by analyzing their empirical relationship with vegetation indices from remote sensing. For example, in this graph, Kc is estimated by a linear relationship with NDVI. The advantage of this approach is that remote sensing data provides spatial information of crop coefficient Kc, and thus crop evapotranspiration. However, the full procedure of adjusting Kc for non-standard conditions still requires information about the crop, soil, and water management.